Excellent. We see you. Can you share
Great.
screen, please? I'll let you know when you have 5 minutes left.
Okay. Can you see my slide?
Yes.
Okay. Hello, everybody. My name is Cristiano Longarini, and I'm a postdoc at the Institute of Astronomy in Cambridge. And I'm really happy to be here, although remotely, to present my work, whose title is Rethinking about gravitational instability as a planet formation scenario. So thanks to ALMA observation, we are now able to probe planet disk interaction in protoplanetary disks. And in particular, we are able to indirectly or directly infer the presence of embedded protoplanets in protoplanetary disks. For example, we can aerodynamical modeling planet disk interaction in these systems and compare the results of the simulations with the observed morphology, as in the case of the H-tau I'm showing you here. In addition, during the last few years, thanks to ALMA, we have been able to observe in great detail the kinematics of protoplanetary disks. And in particular, it is possible to observe the kinematic perturbations exerted by an embedded protoplanet onto the surrounding gas. And these kinematic perturbations are called kinks, and we have been observing several of them during the last few years. And finally, but just for a couple of systems, it is also possible to directly image the protoplanet or the circumplanetary material, as in the very famous case of PDS-70 or in the case of HD 1691-42. And I mean, this picture is basically telling us that planet formation is a very efficient process, and it must happen when the protoplanetary disk is still young. And what are the characteristics of young protostellar disks? So young protostellar disks are usually more massive compared to more evolved ones. And this is also an observational evidence, as I'm showing you in this plot, where there is the cumulative mass function of protoplanetary disks in different star-forming region. And what we can see is a trend of this quantity with the age of the star-forming region, pointing to the fact that young protoplanetary disks are more massive. And of course, this makes sense since they are accretion disks. And when a protoplanetary disk is massive, the role of its self-gravity and possibly the gravitational instability is dynamically important. And so the main question of my work is to understand what is the role of self-gravity and gravitational instability in the process of planet formation. So historically, gravitational instability has been proposed as a planet formation scenario back in 1997. And as you can see from this numerical simulation, this is a gravitationally unstable disk that eventually produces a gravitationally bound fragment. And it is possible to estimate the mass of this fragment numerically from the simulation or also with analytical arguments. And usually for typical protoplanetary disks parameters, the mass of this fragment is of the order of 1 to 10 Jupiter masses. So initially, this is in the protoplanetary regime, however, this is just an initial mass. So this fragment will start accreting material, eventually forming a stellar companion rather than a planet. So this classic scenario, gravitational instability, is more likely to explain the formation of low mass stellar companions. And so what I'm doing is to study the interplay between dust dynamics and gravitational instability. In particular, there are two main phenomena that one needs to take into account when studies this, that are dust trapping and the dust excitation. So as for the trapping, since the gas spiral arms are pressure maxima, dust particles tends to accumulate in these structures, significantly increasing the local dust-to-gas ratio, and possibly these spirals are a good location for dust to directly gravitationally collapse, forming planetary cores or planetesimals. But at the same time, dust particles can be excited as a consequence of the interaction with the gas spiral arms. And so this interaction is exciting relative motions between dust particles. So this is stabilizing the dust layer against gravitational collapse. So what we need to do is to understand what is the interplay between trapping and excitation. And what we want to find out is what are the best conditions for dust to directly collapse inside spiral arms. And a lot of work in the past has been done in this context. And here I'm showing you the latest results of my work. So when we talk about gravitationally unstable disks, it is important to remember three main parameters that are controlling the instability. Here, I'm talking about self-regulated gravitational instability, so meaning that the amplitude of the spiral perturbation in gas is constant, and it is not fragmenting, as in the case I showed you before. And the first important parameter is the Tumri-Q parameter. This is a dimensionless number, and it determines whether the system is stable or is unstable. And it's basically a ratio between the stabilizing factors, such as the pressure and the rotation, over the destabilizing one that is, in this case, the disk self-gravity. When Q is Q equal 1 is the instability threshold, and we say that the self-regulated disk is in a Q equal 1 state, and it can efficiently transport angular momentum. The second important parameter is the beta cooling. So here I'm talking about cooling just as a way in which we trigger gravitational instability. Indeed, if we look at the Tumri parameter, this parameter is directly proportional to the sound speed, so to the temperature, meaning that colder disks are more likely to be unstable. And the beta cooling is a very, very simple cooling prescription. So we say that the cooling time scale is proportional to the dynamical time scale, and beta is the factor of proportionality. And it is not at all a realistic treatment of the cooling in protoplanetary disk. It's just a numerical receipt that we use in our simulations to better control the parameter space. And in the self-regulated state, the amplitude of the spiral, so delta sigma over sigma, is proportional to beta to the -1.5, meaning that beta is basically controlling the strength of the gravitational instability. And finally, the third parameter is the disk to star mass ratio. So this is determining the global morphology of the spiral. And indeed, it is proportional to the opening angle and inversely proportional to the number of spiral arms. And this parameter also controls whether the transport of angular momentum is local or it is global. And in this slide, I'm showing you snapshots of gas density of hydrodynamical simulations where I vary the disk to star mass ratio and the beta cooling to show you the different morphology one can obtain by varying these two parameters. And actually, the morphology of the spirals is really important when one studies the dust dynamics in these disks. So as I told you before, the first phenomenon that I would like to discuss here is dust trapping inside gas spiral arms. So these are, what I'm showing you here are snapshots of dust density in hydrodynamical SPH simulations with different Stokes numbers. So here the Stokes number is just a dimensionless measurement of the aerodynamical coupling. So low Stokes number means that dust and gas are coupled, while high Stokes number means that they are uncoupled. And so if we look at very low Stokes numbers, so 10 to the -3, 10 to the -2, in this regime, the dust is following the gas. And we can see that the gas is tracing the spiral arms since also the gas is doing it. Then in the intermediate regime from Stokes 0.1 to Stokes 1, we see the strongest effect of dust trapping. Indeed, the dust spiral arms are thinner, and the concentration of dust is really high. And since the effect of trapping is the strongest here. And finally, for Stokes number higher than 5, let's say, we see that the aerodynamical coupling is less and less, more and more weak. And you can see that the spiral pattern tends to disappear by increasing the Stokes number. And so the second phenomenon is the dust velocity dispersion, so dust excitation. And here I just want to briefly show you what's happening to understand what are the scalings of this phenomenon with the parameters of the instability. So we can consider a dust grain that is interacting with the gas spiral arm. And during the interaction, we can imagine that the spiral arm is kicking the dust grain. So it's exciting a motion in dust grains. And of course, the degree of excitation of this dust grain depends on the spiral parameters. And in particular, it depends, first of all, on the Stokes number, because it says how much dust and gas are coupled. It depends on the strength of the spiral, so the delta sigma over sigma, that is the strength of the kick, and then the number of spiral arms, that is basically the number of kicks the grain receives. And if we remember the scaling I discussed before, we can easily say that dust grains are efficiently excited when they receive a stronger kick, so for low beta, and for low dist-to-star mass ratio, and the opposite for the other parameters. But here, as you can see, I'm not discussing the Stokes number because I'm doing it now step by step to study the different degrees of aerodynamical coupling. So, thank you. So in the low Stokes number regime, so for Stokes number lower than 0.1, the velocity dispersion is mainly controlled by the viscosity because it's the dynamics of dust and gas is almost the same. And at the same time, the dust trapping is negligible because the two components are strongly coupled. Then we have the most interesting regime that is from Stokes 0.1 to Stokes 1, where the velocity dispersion reaches its minimum, and mainly because there is a velocity correlation of dust grains inside spiral arms, and so the relative motions are not big enough. And as for the dust trapping, here it is we can observe the strongest effect of dust trapping, and so these are the best conditions for dust collapse inside GI spiral arms. Then for Stokes higher than 1, let's say from 1 to 10, we see that the velocity dispersion increases because of the spiral kicks, as I discussed before. And there is a scaling with the square root of Stokes number. And the dust trapping becomes less efficient because the aerodynamical coupling is weaker. And finally, for Stokes higher than 10, basically the velocity dispersion is just controlled by eccentric motion in the dust that are generated by the gravitational interaction with the spirals, and dust trapping basically does not happen because the drag force is 0. And so here I just showed you like the results of these numerical experiments studying different regimes of Stokes number. But when we put all this together in, let's say, in a more realistic simulation, what do we get? So here for more realistic simulation, I mean a simulation where I don't fix the Stokes number, but I fix the grain size. That is, I mean, more realistic is not, of course, what is actually happening, but it's a step further to the closer to the reality. And so we observe that in such a simulation, dust collapse happens in the for the parameters we expect. So in the high dist-to-star mass ratio regime, for the long cooling, and when the Stokes number of dust particles is of the order of 1. And so you can see from this snapshot, on the left, there is the gas, and it shows the spiral pattern. And if we look at dust particles that are the yellow points here, you see that there is dust clumping. So dust is actually collapsing inside this spiral. We verified that this clump is gravitationally bound, and it is. And we could compute the mass of this clump from the simulation, and it is of the order of the Earth mass, so in the planetary core regime. And finally, if you look at the plot on the right, you can see that the collapse is happening just in the dust, so that is the orange line, while the gas density remains constant, meaning that here the planetesimal is just made up of dust. And yeah, so this is just a slide to show you what I am working now, so as a future perspective of this work. So during this conference, we've discussed a lot about infall, and here I'm showing you a simulation in which we try to implement a very, very simple infall prescription in SPH. So we are just adding SPH particle at a given radius at Keplerian velocity with a fixed mass injection rate. And we see that this injection is triggering gravitational instability, of course, And when we study the power spectrum of the spiral and we compare it with the cooling-driven case, we see that the spectrum is quite different. Indeed, in the infold-driven GI regime, we have most of the power concentrated in the dominant modes, and we don't have power in high M modes, while we have it for cooling. And since I showed you that the morphology of the spiral is really important for dust dynamics, our question now is to understand what is actually happening into dust in these kind of simulations. So here I leave you with my conclusion. So I won't go through the points because of the time, but the next talk by Phillips will be very interesting because they actually observe dust clumping inside the spirals in a GI disks. So I really suggest to listen to the talk. And with this, I thank you very much for your attention, and I am happy to take questions.
Thank you very much, Cristiano.
Thank you.
For a change, we're going to start with a question from the Zoom.
Okay, it's a question from Eleonora Fiorellino. Hi, Cristiano, thanks a lot. Very interesting talk. To my knowledge, there are problems with the measures of M-disk for protostars because of the envelope contribution and because of the optical regime, which is not known. Are models able to help us with that?
So, the question is how to measure the disk mass, basically, in young disks. So, yeah, of course, I mean, measuring disk mass in protoplanetary disk in general is difficult because of, I mean, because we can't actually observe most of the material that is there, that is molecular hydrogen. And I mean, as I told you here, we expect protoplanetary disks to be gravitationally unstable during the first stages of their lifetime, when they are usually embedded into clouds, and so we can't really observe what's happening there. So yeah, I think that this is, I mean, the biggest problem here is that it's very difficult to observationally probe this part of the disk lifetime, mainly because of cloud obscuration. So yeah, this is a problem, and hopefully in the future we will be able to probe better these disks.
So Patrick, then Lee, then Trolls.
I just have a small follow-up on that. It is, I mean, you can get the dust mass for young disks, or you can get the dust flux for young disks very well. How that turns into a mass is very dependent on how you do the conversion. So what you showed was just the usual flux to dust. If you do radiative transfer, it actually ends up turning around, and you end up with the young disks being less massive. I'm not going to hang my hat on that being the final answer. It's just to say that we can actually see the compact dust disk emission. The gas is a lot harder to do because of the envelope.
Yeah.
But we can.
No, I agree.
How that turns into a dust mass then becomes a matter of how you convert from a flux to a mass, and there's a lot of uncertainty there still.
Yes. Also, I mean, usually dust masses measurements are made under the hypothesis of optically thin dust emission, and I don't think this can be true for young disks. So yeah, I mean, it's not super simple how to obtain dust masses. Yeah.
Yeah, if I could just add to that, in addition to what Patrick said, let's remember that we're basically measuring the millimeter dust mass times some correction factor, right? So it's a limited size range that, in addition to the optical depth effects. But I wanted to ask you, are these 2D or 3D simulations? Because I thought that if you had settling, you could actually help generate enough settling, you could generate a vertical velocity shear, which could add to the turbulence and maybe affect things.
So all the simulations are 3D, and we of course observe dust settling that is in some way helping the dust collapse, because I mean, if the dust layer is thin, that means that it's colder, so it's I mean, the velocity dispersion is lower, and so it is helping to dust to collapse inside spirals. Yeah. So the simulation takes into account also vertical motions.
Okay. Yes. So I have a question about your model. Is it fixed Stokes number particles, or actually physical particles that change Stokes number when they get into the dense region? And the second thing.
Yeah. No. Go ahead.
if you have estimated the optical depth of these blobs when they start collapsing, can they actually cool, especially for the dust? Will it survive?
Okay, so to answer the first question, so these simulations I'm showing you here and the ones that I used to obtain these plots, I'm fixing the Stokes number. So the Stokes number is fixed throughout the disk. As I said, this is just a numerical experiment. It is far from being true and to be realistic. And this is just to better study what's happening, let's say, Stokes for different regimes of Stokes number. While for the simulation, for this simulation where we observe the dust clumping, here I'm fixing dust grain size, so the Stokes number changes according to the total density of the simulation. And as for the second question, so this is something I haven't done actually. And this simulation, we don't have any, let's say, radiative transfer calculation, meaning that the only thing we are doing is to trigger gravitational instability with cooling, but this is just a dynamical thing. So we are just decreasing the internal energy of the SVH particles. And I think it would be very interesting to study also the optical depth of these clumps to test, as you suggested, the cooling or also maybe the observability of them. So thank you very much for the suggestion.
So I think we're running out of time. Any chance we can move all the questions to the Slack channel, please? And now let's continue. We have